All right, welcome back to 353. There we go, I got it out. Sorry, I got harassed by a bunch of first years. We went over strings for the first time and buffer overflows and all that fun stuff. So yeah, lots of questions. All right, speaking of lots of questions, let's explore more locks. So where did we leave off last time? So we were trying to implement a lock and we were failing at it quite spectacularly. So you can implement locks in software with actual minimum hardware requirements. So the minimum hardware requirements you actually need to ensure is loads and stores are atomic and instructions execute in order, which doesn't sound that hard. But for modern CPUs, executes never execute in order, which at least one of you knows. So there's two main algorithms you could use if your computer has these two requirements. Peterson's algorithm and Lampard's bakery algorithm, which is basically like taking a number at a bakery store, which a lot of you probably have never done. So we will just skip them. They don't really scare well, and processors execute out of order anyways. So we need some help from the hardware. We need some more fun atomic instructions that we can actually use to implement a lock. So let's assume a magical atomic function called compare and swap. And its function arguments look like this. So first argument is a pointer to an int that it's trying to modify the value of, and it's trying to modify the old value to that new value. So this function will always return the original value pointed to, and it will only swap if the original value that it reads is equal to old, and it will change it to new. And it will always return the current value of it. So this function is atomic, so it will either happen all at once or not at all. So if we give our lock another shot, we could do something like this. So again, our init, we assume we're just going to use an integer to signify whether or not some thread has acquired the lock or not. The value of 0 means it is unlocked. The value of 1 means some thread should have had that lock. And we want it to work in such a way that only one thread can call lock and make it through the lock call at one time. So this is our new attempt at it. And the problem we had before, right? We could come up with a way two threads could call this lock function and both threads could make it through. And that was because, well, they both originally read the initial value of 0, and then they operated locally on that old stale value, and they both passed this lock function. So now what happens if initially the lock value is equal to 0, and I have two threads, let's call them thread 1, and I have thread 2. If they both call this lock function, only one can run first. We're just assuming concurrency here, and we could get interrupted after any single atomic instruction. So this while compare and swap, again with this semicolon at the end, means that if it's false, it's basically an infinite loop. So let's say thread 1 executes first. So if thread 1 executes first, then it will just immediately run this compare and swap function. So it will take this pointer, we're assuming that L is a pointer to this lock, and try to atomically swap the value from 0 to 1, and it will always return the original value pointed to by that pointer L. So in this case, the compare and swap function will return 0. So this is the original value. Again, this is atomic, so it's atomically going to return that value 0. And in this case, because the old value is 0 and the current value is 0, it's going to atomically change that value from a 0 to a 1. So this thread 1 will compare and swap, set that value from a 0 to a 1, and compare and swap is going to return 0. So while 0 means while false, means it will break out of the while loop and then pass by that lock call. So now if thread 2 executes next, right, it only did one atomic instruction. It could have been interrupted before or after because it's atomic. Now, if thread 2 calls this compare and swap function, well, again, since this is atomic, it's going to look at the value pointed to by p, which in this case is 1, and the result of this compare and swap is going to be 1. And it will only change that value pointed to if the current value is 0 and it will change it from a 0 to a 1. So currently the value is 1, so compare and swap is going to return 1, and it's not going to do a single thing. So this will just return 1, and then it will just continue looping. So while true, it would just continue looping, continue looping, continue looping. There's no way it could ever pass by this lock call until eventually thread 1 that has the lock right now has the lock, because it was the thread that went ahead and changed the value of the lock from a 0 to a 1. Thread 2 will not be able to make progress till eventually thread 1 calls this unlock function. Again, it is the only thread that changed it from a 0 to a 1. It's the only thing that could be running this unlock if we properly have our critical section sandwiched by a lock and unlock. So eventually it's going to change that value to a 0. And then when thread 2 now eventually gets to run again, it will be able to pass by this compare and swap, because now the value pointed at is 0, and it will go ahead and atomically swap it from a 0 to a 1. Thread 1 has released the lock, and now thread 2 could go ahead and it now has that lock, So it would be able to pass by the lock function, no problem whatsoever. So does this seem like a good implementation of a mutex? Any issues with it? Or is it perfectly good and yeah, we're great? Yeah.
There is the whole infinite loop on the lock on the waiting process.
Yeah, there's a bit of an infinite loop problem where, hey, if some thread is trying to get it and the current value is 1, why bother trying to get it again and again and again and again? So it works. It's an implementation that works, but it's not the greatest. So what we implemented is essentially something called a spin lock. So that compare and swap is an atomic hardware instruction on pretty much every single modern CPU. On x86, it's called comp exchange. Why? Short for compare and exchange. Again, they have to make things short to be cool, I guess. So it can be called compare and exchange, compare and swap, basically synonyms. So this implementation works in that it is safe. It's not super fair, and it has that busy wait problem where we have an infinite loop. So if we have a uniprocessor system, so something with only one physical core, then if we can't get the lock, one thing we should obviously do is if you can't get it, and there's no point just trying again and again and again, I should just yield. I should just give up my CPU time, let another thread make progress, and hopefully that's the thread that has the lock, and it is something that the kernel can schedule, and then it eventually calls that unlock. On a multi-processor machine where I have multiple cores, it's not as easy. A spin lock may be okay if that critical section is very short. Maybe retrying a few times isn't that big of a deal. Again, now it just kind of depends. So if I wanted to improve my lock a little bit, I could just simply add a yield, right? So in the body of the loop, I would do while compare and swap, and if it returns 1, which means some other thread has that lock, I can just be like thread yield, I can give up my CPU time. But this actually introduces another problem that is related to fairness. We have a problem called a thundering herd problem. Whoops, apparently that's a link I can click, uh-oh. So, it has a thundering herd problem. So, what that means is that if I have 8 threads all trying to do the lock, conceptually, I know that if I have 8 threads all trying to get the lock, and I unlock, only one of those 8 threads is actually going to be able to acquire that lock. So there's no use to have 7 other threads even attempt to get it if we know that it's not even going to be possible for them to get it. And even if that wasn't the biggest problem we have no control over who gets the lock next. So Thundering Herd, it is a good Boxing Day sale, which hasn't happened for years. You just open the doors and you just let all hell rain loose, which you probably do not want to do. So you want to have control over who gets the lock next. You need to be able to reason about it. So having something like FIFO or just a line is perfectly acceptable. So maybe I add a wait queue to the lock. So here, again, my core logic kind of stays the same. In my lock function, I have while, compare, and swap. If I do not acquire that loop, maybe in this, I add myself to a wait queue, some type of queue that I didn't implement myself, and then I just put myself to sleep. So I sleep, that essentially blocks this current thread until another thread wakes you up. So this is block until someone else nudges you back awake. And then in the unlock function, well, it has to do a bit more work. So it has to set the value of that lock equal to 0, so another thread could go ahead and acquire it. But now it will also check if there's any threads in that wait queue, it will wake up only a single thread. So the idea here is that instead of just letting all hell rain loose, threads, if they don't acquire it, kind of nicely put themselves in line, and then whoever unlocks the mutex just wakes up the first thread in line. So there is 2 actual issues with this implementation, and we should be able to reason about them. Or in this course, it's just assuming a single thread. What is an interleaving of 2 or more threads that causes an output that is undesirable? So in this case, there is 2 issues. One is called a lost wake up. And what that basically means is there a way that a thread essentially puts itself to sleep and then never gets woken up again? So that would be an example of a lost wake up if that situation is possible. And then the other one is the wrong thread gets locked. So if thread 2 is currently at the head of the line, there should be no way that any other thread can acquire the mutex next except thread 2 because it is at the beginning of the line. So the first issue I will have you think about a little bit about how to get is the lost wake-up case. So I'll give you a hint too for the lost wake-up case. Assume that the current value of the lock is 1 and it was set by thread 1. So thread 1 currently has the mutex. So we have thread 1 has the mutex, and then we are going to come up with an interleaving of calls such that another thread puts itself to sleep and doesn't get woken up. So thread 1 that has that lock, I'll give you a hint that it is running this unlock function. So thread 1 has the lock, it's running the unlock function, and thread 2 currently does not have that lock, but it is currently running the unlock function. So I will give you a minute or 2 to think of an interleaving of these threads. Thread 1 that is calling unlock, currently has that lock, and thread 2 that is currently calling lock that does not have that lock. So is there a possible interleaving of these threads such that thread 2 puts itself to sleep and never wakes up, aka, I like saying it just goes into a coma. So I will give you, let's say, I'll give you like a minute and a half to think about it. Alrighty, can anyone guide me to a bad or horrific outcome here? So which thread should start running first for something bad to happen? 50-50, yeah.
So wait, thread 1's the one in the unlock or the lock?
Thread 1 is doing the unlock.
Okay, so yeah, so thread 2
So
compare and swap.
okay, so thread 2 executes first, so it would do this compare and swap. So compare and swap right now, the value of that lock is 1, so compare and swap is going to return 1. So the next thing it would execute is this line. All right, who should go?
Now it switches to thread 1.
So now it switches to thread 1.
And thread 1 completes the unlock, but then the wait queue is empty right now, so it doesn't even wake up anything.
So thread 1 executes, it changes that value from a 1 to a 0. So now the current value is 0. And now what?
It goes back then, and then thread 2 hasn't added itself to the queue yet.
So thread 1 continues. So thread 1 would check. Let's draw our wait queue. So wait queue. Currently our wait queue is empty. So it would check if there's threads in the wait queue. Currently there is no thread, so this will be false. So it will just finish the unlock call. It's done. Now thread 2 will execute, right? If thread 2 executes, next it will add itself to the wait queue. We'll just be nice and assume that that's atomic. So thread 2 would add itself to the wait queue and then put itself to sleep. So now it's blocked. Now thread 2 is asleep. And now, if that's the last time we call unlock in our function, it's asleep forever, right? It was put to sleep and now it's gone, it's in a coma. Everyone get that? So, let us rewind a bit and go to the next bad one. So, next bad case. Oops. So next bad case is the wrong thread gets that lock. So I will rewind a bit and create a new situation with you. So this will be slightly easier than an exam because I'm giving you a good situation. But let's assume we are in the current state of something like we had before. So we had the lock value was 1, and thread 1 was the one that locked it. So thread 1 has the lock. And it's calling this unlock function. Let's assume that we already have thread 2. And thread 2 tried to get that lock, right? It did the compare and swap, it got 1. It added itself to the wait queue. So it added itself to the wait queue. And since it's added itself to the wait queue, it should be the next thread that acquires the lock when thread 1 eventually unlocks it, right? So let's also assume we have this pesky thread 3. So let's assume we have thread 3, and thread 3 is the one calling this lock function. So in order for the wrong thread to get the lock, there has to be some interleaving of threads such that when thread 1 unlocks that lock, thread 3 actually gets it instead of thread 2, because thread 2 is politely standing at the front of the line. There should be no way that thread 3 kind of swoops in, butts ahead in line, and acquires that lock. So I'll give you another minute to think about what interleaving of, in this case, since thread 2 is blocked because it is currently asleep. So interleaving between thread 1 and thread 3 such that thread 3 acquires that lock instead of thread 2. So again, I'll give you another minute to think about that. Alrighty, who can save me? Yeah.
So thread 1 will execute and set L to 0.
All right, so yeah, first one, let's assume thread 1 runs first. So it changes that value of the lock from a 1 to a 0. So it is essentially given up that lock. Yep.
And then thread 3 checks the lock.
Yeah, and then we immediately start executing thread 3, right? So if thread 3 executes next now, so it would check that value of the lock. Currently it is a 0, so it will happily change the value from a 0 to a 1 atomically, right? And now thread 3 has that lock. So thread 3, this would return 0, it would pass by, and it's done already. So it just immediately swooped the lock, butt ahead in line, and that was it. That was pretty quick, right? So what's going to happen now if we assume that, hey, thread 3 is now done, thread 3 has that lock? Well, we can play this out just to see what would happen. Nothing bad is going to happen other than the wrong order of threads is going to happen. So what's going to happen if we continued on with this, thread 1 is going to, if it's picked to run again, check for threads in the wait queue. Currently, thread 2 is in the wait queue, so it's going to wake up one thread. So it would remove this from the wait queue. It essentially would get unblocked, and it essentially would return from this thread sleep function. So since it returned from thread sleep, looks like it returned from thread sleep, so it's in a while loop, so it'll go back up. Check this condition again. So compare and swap in this instance, it'll do something that it didn't expect, but not wrong. Check the current value. The current value is 1 because thread 3 has it, so it'll just re-add itself safely to that wait queue, and then just go back to sleep again because someone else has stolen its lock. So nothing bad happened other than the wrong order of threads occur. So now it's back asleep again. So any questions about that? All right, perfect. So those were our 2 issues that we need to fix. We need to fix that lost wake up and the wrong thread getting the lock. So here is an interleaving for the lost wake up, just so you have it on the slides. And again, here's an interleaving for the wrong thread getting the lock. So if we were to fix it, I'll just, skip ahead. So this is how we would have to fix it. So this is our implementation that could fix it. So this has a few things going on. So like we had before where there was an integer keeping track of the current value of this mutex, whether it's locked or not, we still have that. It is called int lock, and it is in this mutex struct. So we're going to need some other things to keep track of in this mutex rather than just the variable. So we're going to have this int guard. So this will be used internally as a spin lock. So we essentially had a data race before. So in order to fix that, we're going to use a spin lock internally because it worked. It had some problems where, has a busy wait problem. But in this case, we're assuming we're using a multi-core machine, and these functions are pretty small. So we're going to use it internally as a spin lock. And then I'm also going to represent this wait queue as just a q_t. So our implementation, in order to read it, what I'm going to do is this while compare and swap of the guard, that essentially is just a lock of the spin lock. So in order to make this a bit more readable, I could just go ahead and replace this, replace this compare and swap of the guard, just get rid of it. And in order to read this, I can assume it's pretty much the equivalent as like a spin lock call for the guard. Or to shorten it, it's just a lock of the guard. And then whenever I set the guard equal to 0, that's the same as unlocking it. So I can change this if I want. Guard of 0 and guard of 0. So these two things are essentially the equivalent of unlock guard and unlock guard. So now the idea is in the lock, I acquire that so that only one thread can, like it essentially makes the whole thing a critical section. So only one thread can make progress in this lock function at once. So because of that, I can go ahead and, oh God, that's not going to work, is it? So because of that, I can just immediately check the value of the lock, and I don't have to protect that because now I know I'm operating under mutual exclusion. I don't have to use compare and swap in this case because I'm the only thread that can be doing this. So there's two cases. If the lock is currently unlocked, I just acquire it. I change that value from a 0 to a 1, and then I just unlock that guard. That's the only thing I have to do in the case that no one else is waiting for it, or sorry, in the case that is not locked already. Otherwise, if it's already locked, this line is essentially add self to queue, and then it unlocks that guard so that another thread can actually make progress and either do the unlock or the lock call. So then it puts itself to sleep, and in both cases, the if, right, we unlock that guard. Then in the unlock call, again, we can go ahead and make this a little bit more readable, where this compare and swap of the guard, that is essentially the exact same as a lock to guard. And this at the end, whenever we are changing the value of the guard from a 1 to a 0, that is the same as, let me get rid of it, that is exactly the same as unlocking the guard. So the rest of it is a critical section. So now, if we have a thread that is unlocking, locks the guard, make sure no one else can go ahead and add themselves in the queue. Check if the queue is empty. If it is empty, then just release the lock. No one needs it, so it would change that value from a 1 to a 0. And then otherwise, we can, since this is Test. Whoops. Alrighty, so back on track. So we have locks now in our toolbox. They ensure mutual exclusion. Only one thread at a time can execute between the lock and unlock calls. Doesn't really help us if we need to ensure ordering between threads, so that's going to be our next thing. So how do we ensure order between two threads? So let's have this problem where we have two threads. Thread 1 is executing this function called print first, and it prints off this is first. Thread 2 prints off or runs this function called print second, where it prints off I'm going to second, and we want thread 1 to always go before thread 2. So also recall here that now if we have two threads all executing at the same time, we have to make sure that the functions we use are something called thread safe, which you would need to ensure. So if I look at the documentation for printf, I haven't done this before, but if I look at the documentation for printf, if I do man printf, and I go all the way to, oh, that's not the right one. If I do man 3 printf, yeah, that's the C standard library one. If I go to attributes, I can see that it says, gives me all the interfaces, so it gives me all these function calls, and then it's so important that they have this separate little attribute here called thread safety. And the value is MT safe. That's multi-threaded safe. So this function is thread safe. You are allowed to call it with multiple threads as just a little issue. So if it wasn't thread safe, one implementation of printf for that whole string could be like this. It could be 3 separate write system calls that we can assume are atomic, but it could be like, this is first, I'm going second. So if I use this and execute this program where I'm assuming printf is not thread safe, and I run this, was it safe print? I should see something weird like, I'm going second is first, because I don't know what the order between the two threads are. I only know that between one thread, it will go in order. So thread 1 printed this, then thread 2 executed, printed I'm, then going, then second, and then the first thread came in and printed this is first. And again, when I execute this, I will see, might get lucky. This is first, I'm going second, in which case I have no bugs. Still have no bugs, still have no bugs, still have no bugs. Wow, what the hell? Oh, this is first, going second. This is going first, second. So this is what would happen if printf was not thread safe. So how would I make this thread safe if I wanted to make sure this is thread safe? What would I need to do? Yeah, create a mutex and then just have a lock and unlock around the 3 writes from both of them so that I'm guaranteed that I see a single line at a time. So thankfully for us, printf is thread safe. So because it's thread safe, I will see the whole line all at once. So now if I have this program called order print, what I want is to make sure I always see this is first and I'm going second. If I run it a few times, I can see that, hey, it works right now, no bugs whatsoever. If I run it a few more times, this is first. Oh, there we go. Unlucky. So, anyone have any ideas how we could guarantee that this is first prints all the time and I'm going second prints next? Yeah?
Use some variable that the one we want to a second has to wait for a specific value, and it can only be set by the one that comes before it.
Yeah, so we can basically create a variable like, oh no, like a flag or something like that. And then have this thread, I don't know, set flag is equal to 1. Oops. And this thread wait until thread is equal to 1 or flag is equal to 1 before progressing, something like that, right? So yeah, we could do that. We have to, in general, we'd probably have to protect against data races and things like this, but probably fine in this case since we only change that value once. So what we are going to use is something more general, but that same idea of a flag. So we're going to use something called a semaphore. So a semaphore, anyone know what that word actually means in normal English? Has anyone ever heard of this word before? Any maritime people? Anyone like big boats? No? So, yeah. Yeah, that's the thing where you hold flags. So for shipping or ships, I don't know, I'm not a super boat person. In order to synchronize or ensure ordering between boats, like if you have huge shipping ships, probably important to make sure actual wave in the air flags that have different symbols on them that you wave to other ships to signify your intent, and then they reply with another flag and they mean something. It's basically making sure you two are synchronizing yourselves and going in some order. So we stole that word in computer science and we use it for signaling between threads. And our signaling between threads is just what order things happen in. So semaphores, unlike ships, are a lot simpler for us. They just have a value, and that value is just an integer value. In fact, a integer value greater or equal to 0 that's shared between threads. So it could optionally be shared between processes if you want to ensure ordering between two processes. But for this course, we're just going to care about threads. And the way that a semaphore works for us is it thankfully only has two fundamental operations. They are atomic, and they are quite easy to reason about. So a semaphore, just think about as just an integer, and the wait function will decrement that value atomically, and the post operation will increment that value atomically. And that's basically all there is to it, except for one simple rule. So wait blocks until that value is greater than 0. So wait will guarantee that it actually decrements that value, and that value will never be negative. So if the current value is 0 and some thread calls wait, well, if the current value is 0 and it's not allowed to go negative, it will not decrement 0 to -1. It's going to wait for another thread to increment it from 0 to 1 before it is allowed to decrement it, probably from 1 to 0. So how they work is initially I can set that value to whatever you want. The way to think about it, and we'll get some practice as well, is that that is the number of wait calls that can occur without blocking, without any post calls being required. So semaphore API is similar to pthread locks. I include semaphore.h, and to initialize it, again, I have to give it the pointer to the sem_t in order to initialize it, and it has a few other variables. So this int p shared, that signifies whether or not this semaphore should be shared between processes. So that controls what happens when you fork. So if I fork and p shared is 1, then my new child process will have the same semaphore. Any changes that happen to it will be reflected in both processes, so I can use it for inter-process communication or ordering between processes. But for this course, we're just going to set it to be 0, so that is independent within a process. And then the next value is unsigned int value, so that is the initial value of the semaphore. And then since we have an init, we have a destroy. And then we have the wait function. So again, wait will decrement it, and it will only decrement it. The special rule is if that value is going to be greater than 0. So it's not allowed to be negative at any point. And wait will block until it can decrement it. Like we had a try lock before, there is a try wait. So that is a non-blocking version that will tell you whether or not it was able to decrement it, yes or no. Then we have post, which is just a fancy, fun word for incrementing. So all these functions will return 0 on success. Minus try wait, we will probably just ignore their return value and assume they always return true, or return no errors. So if we want to make sure one thread always prints first, we can use a semaphore, which just kind of takes that flag idea. So if we want to do this using a semaphore, how I like to do it is, well, for this we need to ensure some type of ordering between these threads. So I need to create a semaphore. I'll call it just sem because I am very creative. We have to include the library, so include semaphore.h. So I create a semaphore called sema because, again, I'm creative. So the first thing I find the easiest if we want to ensure order is first you want to place the wait call. So if I want to place the wait call, I have to think about, well, what do I want not to happen? And in this case, what I want not to happen is I don't want the second thread, if it gets picked to execute, to print I'm going second until the first thread is done. So what I could do is, first thing I can do is place my wait call here. So I want to wait on the semaphore until something happens. Oops. So after I wait, the next thing I like to think about is what the initial value should be. So here I have to initialize my semaphore, so I could do sem init, give it the address of sem, p shared is 0, and then I can think about what the initial value should be. So the initial value should be, the way to think about it is how many threads can actually pass by wait without a single thread calling post. So in this case, what probably do I want the initial value to be? 0, right? So if the initial value is 0, right now, how we have it set up is we create 2 threads. They could execute. We don't know which one is going to execute first. So right now, if print second were to execute first, and now we added the sem wait, and the initial value is 0. So if the current value is 0, then this wait will block until it can actually decrement that value, so that it will wait until it's greater than 0. So this will wait. It will block until, in this case, someone actually posts to it. So now the next thing to do is to place my post. Where should I place post? Yeah. Yeah, after I print this is first, right? Whoops. So after I print first, I can post that semaphore. So this will be blocked. It will be waiting. And then the only way now for the second thread to print I'm going second is the first thread has to print I'm going first, then post, which would increment the value of that semaphore from a 0 to a 1. And now the second thread, if it gets picked to execute, it could be unblocked, and then decrement that value from a 1 to a 0, print I'm going second, and now I'm guaranteed that that order happens. So I can compile this now, and then check that indeed, no matter how many times I run it, I will always get this is first, and then I'm going second. And I also have the added benefit that if I had some more code here, so more code in these threads, that aside from the ordering, so this is first and this is second, the more code in both the threads could run in parallel as well, which would be nice and good. I only want a bit of ordering, just ordering between those 2 print statements. So any questions about that? All right, so I will give you this brain teaser then. So I argue to you that I do not need a semaphore. So I already have these mutex things. So why don't I just create a mutex and I use it like this? So initially, that mutex is going to be unlocked. So what I'm going to do is in my second call, I'm just going to call lock twice. So I'll call lock twice. So if I get it, and if thread 2 executes first, it locks the mutex, so it acquires that mutex. And then it locks it again, which, I mean, would be blocked because some thread already has acquired the mutex. It's me. And then the other thread runs print first, prints this is first, then unlocks that mutex. So now this lock would be able to pass and then print I'm going second. Yeah?
What if entire print first, finish running first before print second
So the question is, what if entire print first happens before print second even runs? So what would happen in that case? So if print first runs first, we do printf, like this is first, then do the unlock call. Well, kind of looks okay. This is first happened first. That's good. That's our order. But now, yeah, we call unlock. The current mutex is unlocked, right? So we unlocked an already unlocked mutex. You might imagine that does nothing. Then thread 2 executes. It locks, so it acquires that mutex, and then it unlocks again. And now it's kind of screwed because no one's going to unlock it, right? So if I run this, turns out that turns out this is a terrible idea for more than one reason. But if I run it, hey, it worked. Hey, it worked. Oh no, this is a case you said where now it's blocked. The second thread is blocked forever. So the first thread ran, the unlock essentially did nothing, and then it locked, acquired the mutex, and then locked again, but no one else is going to unlock it. So thread 2 gets blocked forever. So this doesn't quite work. It kind of had that same idea, but you should use mutexes for mutual exclusion. In fact, if you read the documentation, this is full of undefined behavior. So it is technically undefined behavior to unlock a unlocked mutex. So technically, if the first thread executes and hits this unlocked, where it's already unlocked, that is undefined behavior. And it is also undefined behavior to have an unlock call happen from a different thread that did not initiate the initial lock call. So in this case, it kind of works, but technically it has 2 instances of undefined behavior, and it doesn't work all the time. So the 2 are not equivalent. So everyone get that? All right, do not use a mutex for that. But, well, it kind of looks similar. So can we use a semaphore as a mutex? If so, how would we do it? So what would we replace lock by? What would we replace unlock by? And what should our initial value be? Because they kind of look similar, right? Yeah?
Could we just make lock a wait and unlock a post with an initial value 0?
Yeah, so they look exactly equivalent, right? So if the initial value was a 0, wait's the same as lock, and post is the same as unlock. Oh wait, initial value is 0. Not quite. So if the initial value is 0 and lock is replaced by wait, then everyone will just block immediately, right? So what should the initial value be? 1, right? So if the initial value is 1 and we replace lock by wait and unlock by post, it's essentially a mutex. So if I wanted to, I could do that and replace a mutex by a semaphore if I want. A mutex is basically a special case of a semaphore. So in that case where we had a data race with counter, instead of using a mutex, what I could do is create a new semaphore, and then instead of lock, I do wait, which would decrement that value from 1 to a 0. If another thread tried to wait, then it would block because the current value is 0, and it will wait until I post it back from a 0 to a 1. And then one thread can go ahead and make progress. So works the exact same. If I use, wait for lock, post for unlock, and the initial value is 1, behaves exactly like a mutex. So it does behave exactly like a mutex. However, it kind of depends on the initial value. So if I change that initial value to 2, does it work as a mutex now? No, that means 2 threads could be doing that counter at the same time, in which case I have a data race. So if I want mutual exclusion, it's easier just to use a mutex because that's what you actually want. In order for a semaphore to be correct, you have to make sure the initial value is correct. And typically, that's further away from the wait and the post call, so it's a bit harder to argue about it. So even though you could use it for mutual exclusion, I would highly recommend you do not do that. All right, so next problem is, let's do this classical problem that is lots of fun. So let's see if we can come up with a solution to the producer-consumer problem. So assume we have a circular buffer. So it is just an array of elements where each slot is either empty with some data or filled with some data. So we have an array. The indices are 0, 1, all the way up to size, or n minus 1, where n is our size. And it's circular because if we make it to the end, we just wrap around to the beginning. So what we're going to do is we'll have a whole bunch of producer threads that should write to the buffer, and the rule is they should write to that buffer if it's not full, because otherwise it would be overwriting data that hasn't been read by a consumer. And the consumer, all it does is read data. So it should not read empty spots in the buffer. It should only read filled slots and take the data out of it. So the rule is, which I'm going to implement for you to ensure we don't have all data races or anything like that, all consumers are going to share an index and all producers are going to share an index. And in both cases, the initial index is going to be 0 and increase sequentially. So we're going to have lots of producer threads, lots of consumer threads, but all the threads will share a common index with their kind, so we don't have any data races or anything like that. So the producers are going to fill up this buffer, and the consumers are going to read data from this buffer, and we'll assume it is initially empty. So this may take a while, so let's see this. So VM. So in this, we're going to need some semaphores to produce some ordering. So I have some boilerplate function here called initialize semaphores that we're going to use. And then in my producer code, so this while try wait thing here, just ignore this because I'm going to use a semaphore to keep track of how many elements I'm producing and consuming. If this was a real producer-consumer question, this essentially would be an infinite loop. So imagine this is just an infinite loop. Just ignore this right now. This is the code all my producer threads are going to run. And what they're going to do is we'll just simulate doing some work. So we need to do something to actually create some data. And then we're going to fill a slot. So this fill slot function is going to write data into that array. And that's all the producers are going to do, is just filling data into that array. And then we have consumers that, again, ignore this line. This, if it was a real program, would be an infinite loop of just going ahead and reading data or empty slot. So what empty slot will do is go ahead and read some information from that array. And then after it reads it, we can go ahead and reuse that slot. So it would have a sleep after it that I simulate. It would doing some work. So it reads some data. It does some work that we assume that can be done in parallel. So if we run this as it stands, I wrote a bunch of other code, and it also has a bunch of parameters you can play with. So it will, num producer is how many producer threads there are. Num consumer is how many consumers threads there are. Num to produce is how many elements we're going to produce in total. And then buffer size is going to be the size of that array. So by default, we're going to produce 15 things, and the buffer size is 10. And then I also had it for fun. We can adjust how long it takes to produce something and how long it takes to consume something. So if we run this right now, I also have a whole bunch of messages that will show me in red letters whether or not I did something bad. So if I try to fill a slot that was already filled, like I'm overwriting data, it displays in red. Or if I empty a slot that is already empty, it also gives me some red display where it shows me I did something bad. So let's assume we have just, I don't know, say we have 10 producers and 5 consumers. If I run that, I saw that I had some red text. So if we go up to the beginning, we'll see that it looks like my consumer threads ran first, where it emptied slot 1, or 0, sorry, but was already empty. Then another thread emptied slot 1. It was already empty. Empty slot 2, it was already empty. Slot 3 empty, slot 4 empty, and that were my 5 threads. Then my producer threads filled slots 9 through 10, or sorry, 0 through 9, which is 1 through 10. And then, well, oh, the next time the consumers ran, that was okay because they read valid data. They missed a few, the first ones, but it seemed to be okay. And then my producer threads now have overwritten that data, so they have overwritten the data in slot 0, so no one was able to read from it until it overwrote it. So that slot is already filled. I shouldn't have filled it. And then same with the rest of these threads. And then at this point, I've already produced 15 elements, so all of my producer threads are done. And then my consumer threads just finished by reading that data that has been overwritten, so we missed out on 5 things. So that kind of clear what we're working with right now? All right, fix it. So any guesses as to how we would fix this to make sure that we do not overwrite any, like we don't fill any slots that already have data in them, and we don't empty any slots that are already emptied? So I'll give you a hint. We have to use Semaphores. This is the Semaphore lecture, and we can use multiple of them. Yeah? So yeah, we kind of need like a queue to make sure that they wait in line if there's nothing to do. Semaphores will be implemented using a queue, so we're going to use Semaphores to do the queuing thing. So,
yeah, no, that's what I meant.
Oh, okay.
Think of like the numbering scheme.
Oh, so you can't think of the numbering scheme. All right, so let's go over. So even these complicated questions, whenever we need to place a semaphore, we need some ordering between threads. So first thing I always recommend doing, I always do things in this order. So I think about what I need to wait for first. So where do I need to place a wait call? And then after I know where to place a wait call, probably gives you a good indication of what I'm waiting for. So then you can come up with a good name for it and then come up with an initial value. So what is one thing I need to wait for in this case? Yeah. Yeah, wait for, well, I need to do some waiting in a producer, right? So I need to wait for a producer to do something. So where do I need to add a wait call then? So if I'm waiting for a producer, yeah. Before the empty slot. So yeah, here if I want my producer to wait for or wait until the producer does something, well, I have to add a sem wait here in my consumer. So now this is a good indication. I need to wait on something in order to empty a slot. What am I waiting on if I'm trying to give a name to that? So conceptually, I'm waiting for what? Yeah.
Product to be ready.
Yeah, I'm waiting for like some element to be filled, or in this case, I'll just give you a name. I'm waiting for a filled slot in this case, right? So I can only empty a slot that is filled. So that gives me a good idea that the name for the semaphore should be something like filled slots or something like that. So that is, whoops, did I mess up? Oh, Vim disabled. Let's not do that. All right, let's enable. So I want to wait for some semaphore called filled slots. So now that gives me a good opportunity that I can create it now. So I'll create it. It's called filled slots. Filled slots. And now the second thing I like to do is come up with an initial value. Let me get rid of that compiler warning. So sem I should look at my laptop, not the lag with that screen. So I want to initialize filled slots value and then initialize it with an initial value. So that is how many threads can make it by the wait call without a single post happening. So in this case, if I leave it blank and I look here, how many consumer threads should immediately pass by this wait call? 0, right? Everyone agree with 0? So if it's 0, that means if a consumer thread gets scheduled to run first, then it will wait, it will block until that we have actually filled a slot, right? So, and it kind of makes sense that, hey, we named it filled slots, and the value is referring to how many slots that are filled. Kind of makes sense. So the initial value of that is 0. All right, well, now we place our post. So where should I place a post? So what indicates that I have filled a slot? Yeah. Yeah, right after this fill slot function, right? So after that, if I do sem post, filled slots, then that should be it, right? So now, if my consumer thread gets scheduled to run first, even if I have 10 of them, they will all wait here. And then say I only have a single producer thread. Well, then it will fill a slot. It will post, so increase that value from an initial value of 0 to a 1. And then only one of the 10 consumer threads will get unblocked, run, empty a slot. All good, nothing bad should happen, right? So let's try that. I shouldn't get the message anymore that I am emptying a already empty slot, right? So if I compile, make sure I compile, and then I run it again. Let's do the extreme case where, let's say we have 1 producer and 10 consumers. So we can see that, hey, that seems to work, right? So we see all the time that even though we have a bunch, we wait in order for our producer to fill a slot. And even though we have a ton of consumers, in this case, it gets filled, immediately emptied, filled, immediately emptied, filled, immediately emptied. So it works all good. We have fixed that issue. We can test the other extreme where we have 10 producers and only 1 consumer. Oh, in which case we get both errors again. But with this, the only error that's actually important is the first error that happens. After that, things go off the rails. So if we scroll up, the first error that happened was not that we emptied a slot that was already empty. The first error was that we filled a slot that was already filled. So now we have to fix that. So how would we fix that problem where we want to make sure we don't fill a slot that is already filled? So again, easiest thing to do is to figure out where we need to place our post call. So any guesses as to where we need to create a wait call, wait. Yeah, before this fill slot function, right? So I need to have a wait call right here. So what am I waiting on? Yeah.
Waiting for a consumer to buy something so that the slot's free.
Yeah, I'm waiting for the consumer to actually consume something so there's actually a empty slot, right? So if I were to give it a name, you can give it all sorts of names. The name I like to give it is just emptied slots, right? The number of emptied slots. So I'm waiting for an emptied slot. Okay, I can't spell. All right, so I should name my semaphore emptied slots. So now I'll go ahead, create it. Emptied slots. And now I have to worry about the initial value, right? Emptied slot. So what should the initial value be? Yeah. Yeah, the number of slots, or in general, the size of the buffer, which thankfully, I have here as a global variable called buffer size. So the initial value should be buffer size. So I could fill up the entire buffer before any consumer threads run, which kind of makes sense, right? So the initial value of emptied slots also makes sense conceptually that if initially all the slots are emptied, then I have buffer size of empty slots. So are we done yet? Or did I forget something? Yeah, I forgot the post, right? Where do I put the post? Yeah. Yeah, after I empty the slot. So now here, I could do post emptied slots. So each time I empty a slot, boom, I just signified I've emptied it. So now I can go ahead, compile this. And the situation that gave us a problem before was we had 10 producers and 1 consumer. So now if I run it, boom, no red text whatsoever. I can see that kind of ran as I would expect. So I filled slot 1. All of my producer threads immediately filled all the slots, but I only had 1 consumer thread. So it was slow. It only emptied slot 0. As soon as it emptied slot 0, then we filled slot 0. And then, while we have lots of producer threads, they'll all essentially be chomping at the bit to insert the next one. So as soon as I emptied it, they immediately filled it, empty, filled, empty, filled, empty, filled. And then eventually, we're done filling all of the elements, and then we just wait for the consumer thread to finally finish everything. And now, no matter what kind of random interleaving of different threads we do, we can see that, again, we'll have no red text. Everything is now properly synchronized, and we have the benefit that, again, this thing where we simulate doing work and simulate doing some work in both cases, that could be done in parallel between the threads. And they're all properly synchronized. They're all running in order. We're making sure that we don't break our buffer or anything. Everything works great. So any questions about that? So took something very complicated, and then we just broke it down. So again, for semaphores, anything you want to ensure the order between 2 different threads, easiest thing to do, create a semaphore. I mean, you'll have to create a semaphore, but easiest thing to do is first place the weight, then give a name to it, then determine the initial value, then figure out where to post. Yep?
What's the try-weight calls doing?
Oh, yeah. So the question is, what the hell are the try-weight calls doing? So in order to make sure that I produce exactly 15 things, I just cheat a little bit and I use a semaphore. So since I'm producing 15 things, I create this producer remaining semaphore that's initial value is 15. And then try weight just decrements it every time, so I'm guaranteed I create this runs 15 times.
Okay.
So
you don't actually consume more total times than you produce.
Yeah, I'm just using a semaphore just as a way to kind of cheat and just like atomically make sure that I don't have any data races. I produce exactly 15 things. So that's why I said kind of ignore that, because I'm kind of cheating a little bit. In a real program, that would just be like an infinite loop. You'd have all your consumers just consuming data, and all your producers just producing data until you reach the end of whatever file you're producing them from or whatever. All right, any other questions about that? Fairly complicated example, but just break it down one step at a time. You'll see in past exams and whatever, if you want ordering between multiple threads, then you're going to have to create a semaphore for each ordering between threads. So there's lots of practice questions for that, and we'll probably go over them again soon in more lectures as some more practice. But as a summary, we use semaphores to ensure ordering between threads. So previously we ensured mutual exclusion. Now we can ensure some type of order. So how semaphores work, they contain an initial value that you choose. You increment that value using the post. It's guaranteed to be atomic, so you don't have to worry about data races. Then you can decrement atomically using that weight function. And the only special thing about it is it will block if that current value is 0 because the value of the semaphore is not allowed to go negative. So data races could still happen with ordering, so you still need to prevent them. That's generally the hardest part of programming. We, again, will have more examples with that. But for now, that is the end of today's lecture. So just remember, pulling for you, we're on this together, and watch out because you might have a data race in lab 4. So some of you have been working on that. Everyone mallocking and fun things like that. Everyone using realloc array. Make sure you don't have a data race because you can have a data race, and it tripped me up before. So a data race is basically using a stale value. So make sure that when you come back from a swap context, alloc array could move your array. Make sure you reread it because it might be stale by the time you swap context back to that location. So that is a major hint and probably the hardest thing you'll have to debug because aside from that, that's the only thing that tripped me up, and my code actually had a bug on it for my first solution. Yikes. So take that word of advice, and with that, good luck.